Hello everyone, Minecraft Defestus here, and in this video I'm going to be talking about my implementation of what's called Hamming codes in Minecraft. So if you're not familiar with Hamming codes, I would highly recommend you watch this other video, which I've linked in the top right-hand corner of your screen. I think you should be able to see that if I remember to put it there. And you could also check in the description, where I've linked this really great video about Hamming codes, about how they work, that will help you understand them really well. And this video will probably make a lot more sense if you see that video first. That was also the inspiration for this. In the real world, when you're trying to transmit data from point A to point B, often along the way, you'll get some sort of interference. Like, for example, considering that all data is stored in binary, if you're trying to send, say, these 11 bits from one side to another side, often you'll get, often one or two of the bits will flip. Like, for example, I'll represent that by cutting off this line. So as you can see in the original, in point A, the information being sent has this bit 5 lit up, but in what is received on the receiver end, bit 5 is not lit up, and that's because there is an interference in the middle. So what error correction codes are is they're basically a way of packaging a little bit of information at the beginning of what the sender is sending, in order for the receiver to be able to evaluate that little information at the beginning, known as parity bits, in order to make sure that what it received is correct, or if it's wrong, to be able to find out where the error is so it can correct it, if that makes any sense. So in this, which is known as a 1511 Hamming code, which will make a lot more sense if you see the video, which I suggested you watch. Hint, you should probably watch that video. There are 11 bits that are being sent out, and there are 4 bits that are what I said are called parity bits. And the parity bits are not things that you as a sender can change. They're things that are calculated in order to match with the data that you're actually trying to send, which in this case is this polka dot pattern that I made. Nice little polka dot pattern. In the real world, normally you'd be sending letters or numbers or something along those lines, because you're sending some sort of actual information, not just a polka dot pattern. But basically, what this what this quite big circuit does is it calculates what those parity bits should be in order for the receiver to be able to calculate if something has happened along the way and where the error is, or to be able to calculate if an error has happened and where it has happened. So, for example, if you say I turn this off, you'll see that this is recalibrated to the new message that I'm trying to send. So it's live updating. And I'll talk later about all of these parts and how they work. I'm just gonna explain for the first maybe 5 or 6 minutes how this all ties together. So basically, the message that you're trying to send, as well as the parity bits, is sent along these 15 lines of redstone. You can kind of see them. I'm going to hop into spectator mode so you can see more easily. But these 15 lines of redstone are what is being sent out of the sender end and being sent to the receiver end. In retrospect, I kind of regret making this whole circuit, basically motherboard, be so misleading, because there is no connection between the sender and the receiver end other than through here. This is the only connection. So if I say, for example, if I make an error right here at position 10, and I turn 10 off, which represents real life noise or a real life error happening, what the receiver end should be able to do is it should be able to detect, hey, wait a second, given the parity bits at the beginning, and given the information, given the parity bits that were sent, I can calculate that there was an error that happened. I can also calculate where the error happened, and I can fix the error. And so that's what this whole section does. So you see, I created an error in slot 10, and this information gets sent out to this, which is really what the Hamming code is. This is the error correction system. This is the error evaluation system, you could call it, because what it does is it figures out that there is an error, and moreover, it figures out where the error is. So you can see this is outputted on, off, which is 1010 in binary, which is 10 in base 10. And also what it has done is it has selected one of these redstone lines. I'll get back to that in a second, because one thing that's important to remember is that the error that I created way back here where this line, which is supposed to be on, has been turned off, and the message is imperfect, that error has continued going all the way along this line. And I believe it's going. Let me check. Where's line 10? This is line 10. So if there was no error, this line would be on. However, this line is off. And given that the error evaluation system has detected that there is an error at position 10, what it has also done, it has triggered a line, one of these 15 lines. I've all designed them to treat a error in a specific place. This is the line representing. This is the line for representing index 10. So what it's going to do is it's going to intercept. It is going to intercept the 10th line. It's going to intercept index 10, and it's going to switch its value from off to on. So think about what this is. This is basically detected with no knowledge of what was originally sent. It is detected that there was an error along the way. It is detected which one it is, and then it has kind of swooped in, intersected it, and then fixed the error. And if you look at this thing here at the end, what this is the corrected form. This is the corrected form of what was received. So even though there was an error, it was able to figure out where it is, and it was able to correct it. And this is the output, which, if you notice, is exactly the same as what was sent, even though there was an error along the way. And that is, at its core, what Hamming codes are. So I'm going to go into detail as to how this whole circuit works together, and how it does what it does, I guess. Though this is the part where you'd really want to watch that video that I recommended you watch before, otherwise this really won't make sense. Okay, so as you know, or as I'm assuming you know, because I'm assuming you know how Hamming codes work now that I expect you've watched that video. Basically these parity bits work by trying to find out how many ones there are in each of the parity checks. And you also probably know why this is labeled 1, 2, 4, and 8 powers of 2. So basically, this section is where the parity checks are done. So all of the each of these I guess layers are almost like floor buildings, or almost like floors in a building. My words are weird. Represents a specific parity check. So for example, this bottom one, which represents parity check 1, which, if you remember from the video that I sent, sort of represents, I don't totally know how to describe it, vertical lines on columns 2 and 4. So what this is taking in as input is all of the bits that it needs to check. And the way that and it's counting how many ones there are, because it wants to see if that's an odd number. We need to make the parity bit a 1, so that there's an even number of ones in that parity check. And that's basically what it's doing, and it's sending whatever it thinks the parity bit should be back over here, and it's setting that corresponding parity bit to be that. Let me talk for a second about how that parity check even works. What it basically is just a chain of XOR gates in order. First, I should probably explain what an XOR gate is. If you're not familiar, an XOR gate is basically like exclusive OR. I'm going to build one quickly right here. In Minecraft, it looks something like... hold on a second. Like this. Oh. Surprisingly hard to try and give commentary and use a keyboard at the same time. That would not be a good streamer. Okay. So, right here, and right here. So these are the two inputs, and that is the output. So what an XOR gate is it's really like an exclusive OR gate. An OR gate is really one of the simplest things to possibly make in Redstone. You can honestly just build it like this, or something like, want to be slightly more fancy, like that. Where if any of these are on, the final thing is on. This is an inclusive OR gate. So if both of these are on, that's still on. However, with an exclusive OR gate, exactly one of the inputs has to be on. So as we can see, if one of the inputs is on, it's on. If the other input is on, then that's on. If both of the inputs are on, however, it is not on, and that is what makes it differ from that. it is exclusive in that way. It requires that exactly one of the inputs be on, whereas this doesn't care. This just cares as is at least one of the inputs on. And one thing that XOR gates are actually extremely good at, which I discovered while making this, is that they're very good at and I don't totally know how to describe this. They're very good at intersecting a signal, at intersecting a signal and inverting it. So if we have a signal running through here, if there is no intersecting signal, or if the intersecting signal is off, then this just keeps going along on its merry way. Speaking of that, Merry Christmas. And this keeps just going along on its merry way. However, if the interceptor is on, then that will turn the result off, or not even just off. It will just change it. It will change it to be the opposite. And this is actually extremely good for doing the parity checks, because in parity checks, what you're trying to do is you're trying to find out how many ones there are. You're trying to find out how many ones there are. So if there is a and so if you chain up a bunch of XORs like this, and you create an odd number, of inputs that are on, then you'll see the result is that it's powered. However, if there's an even number of inputs that are on, it is unpowered. This is extremely convenient because this is literally what we're trying to do. We're trying to see whether or not there is an even or odd number of inputs that are on. So this is basically what is used to do one of those parity checks, and it's used for all four, because the only difference between each of the parity checks is that you're checking different bits. And so each of these parity checks, like for example, this is parity check 3, which, if you recall, does like rows 2 and 4 basically. So the only thing that differs is the inputs. So this takes the inputs from all of rows 2 and 4. For example, if we look at bit, what's that? That's bit 5. Yeah, you can visualize that's in row 2. And so I've just calibrated all these parity checks to do exactly the right bits. And as always, when it decides what the parity bit should be, it just sends it back along the lines and moves it down to the parity bit. So that's how that section calculates what the parity bits should be. It's really quite a simple circuit. And then that's all that the sender has to do. That's what the sender has to do. It just has to figure out what it wants to send. It just has to figure out what the actual valuable information that it wants to send, and then it has to figure out what the parity bits should be. And so it just sends all of those out in this in all of these 15 I guess lines basically. Here's the thing that I broke earlier. And then what it does is or actually I'm gonna keep that broken because this is what the program is supposed to fix that, so it's pretty relevant. So then basically what it does is, and I won't totally go into why this works, because if you saw, actually I should mention, it would be very helpful for you to look at the part 2 to the video that I suggested you watch, because that really talks more about this part of the algorithm right here, and how XOR gates and like bitwise addition relate to this, because that's precisely what I'm doing over here. So basically, after you receive all those inputs, then what you want to do is you want to add up through bitwise XOR gates the binary values of every line that is on. And that is effectively what this system over here does. So these XOR gates basically can add up all numbers 1 through 15. However, they will only add up the number if its line is on. And you could probably tell how this works in being able to add up all numbers 1 through 15, because these are literally just a bunch of XOR gates. And if its line is on, then these pistons will be pushed up. And so there's no piston that can be pushed up there, none there, but there is one there. So that represents 1. Over here, there's 0, 0, 1, 0. Over here, there is 0, 1, 0, 0. We can see that over there. Because I was cloning this, there's actually pistons on everything. There's actually pistons that could push up on everything. It just depends whether or not there's a piston that's connected to this redstone line over here. So that is 0, 1, 0, 0. That represents 4. That's 1, 0, 0, 0. That represents 8. And you can see why a number will only fire when its corresponding redstone line is on, because none of those pistons will push into there and will send up that. One thing to keep in mind is that this is basically the same as the interceptor over there. which kind of makes sense. And so the next thing to talk about in this is the result. So this is obviously just the result of the addition. Sorry, I should say the next thing to talk about is the interpretation of the result. So after it's added up all of the numbers which are on, what it has to do is it has to interpret that number and convert it into one of these lines. So what this effectively is, it's sort of like a dictionary. It's sort of like a dictionary for the it's sort of like a dictionary to interpret this number and turn it into one of these lines. So for example, we see this number is 7, and the line which it has triggered is this line. And let's take a look at why that happens. And it really makes sense because as we can see, this one is on, this one's on, this one's on, and this one's off. So the only way that this line could be on is if this piston is pushing down, if this piston is pushing down, if this piston is pushing down, and if this piston is pushing down, obviously, in order to send the signal through. I should have explained that. But also this one would need to be inverted, because keep in mind there's no power coming through this line right over here. So there needs to be some kind of torch here to invert it. So that way, in order for this line to be on, effectively, this has to be on, this has to be on, this has to be on, and this has to be off. Which serves as a really good check to check if an exact number is present. And so for all of these lines, I have calibrated their pistons and whether or not there's a torch in front of the piston to be for whether or not a certain bit needs to be a 0 or a 1 in that number, if that makes any sense. Anyways, so after that correct line goes in, after that correct line is triggered, the signal gets sent along here. And then this is where what I was saying about interceptors really comes into play. Because if a line is on, first I should explain, all 15 of these lines are continuing going along there, and all of these other lines here I've lined up to be to perfectly intercept with all of the lines sent out by the sender. So if one of these lines are on, the interceptor will trigger, and it will invert one of those lines, which effectively corrects the error. And you can see this is just a standard XOR gate. On one side is coming in what is sent out of the sender, and on the other side is coming in what is coming out of, I don't know what to call that system, the number evaluator, I guess I'll call it. That sounds nice and fancy. But you can see how this works out really neatly, because all of these correspond to one of these lines, and all of them are able to be fixed. It's just only the lines that need to be fixed are fixed, and so that is what spits out the correct result. In order for the entire thing to run, at first flipping these, first you setting the message to be sent, to be fully processed and for your output to be spit out, it takes about 10 seconds, which is not good, because that's a very long time in Minecraft Redstone terms, considering that a repeater only lasts like a tenth of a second. 10 seconds is a very long time. Part of that is because it's all of this redstone running through this entire thing, running through this entire section right there. I don't totally know the dimensions of this, but you have to actually have a decently high render distance in order to run this entire thing, and have all of the redstone be loaded, because if it's not loaded, that part won't power. I know there's definitely more efficient ways of doing this. This isn't a super efficient way. This is my first time really making a big redstone circuit board like this, I guess. It's less like what I normally do. Normally I'd make like a piston door or something, but this is closer to, I guess, electrical engineering sort of. But yeah, that's how the whole system works. One thing to acknowledge is that in the video that I sent you, the guy talks about how there you can use a 16th bit as sort of a verifier for multiple errors. And admittedly, this is not good with multiple errors. It generally doesn't work. I think it works. It's only worked like a couple of times, but this system really is not good at fixing multiple errors. So, however, using that 16th-bit method that he talked about, you're able to detect for multiple errors, and I believe that you're able to make the system work for I think 2 or 3 errors, and that number expands depending. I believe that number expands depending on how big the input you want to make is. So this system can only really account for 1 error, but that number will greatly increase if you increase the number of the size of the input that you want. This is, I believe I mentioned before, this is called a 1511 Hamigrid because there are 15 total things that are being outputted, and 11 of them are things that you actually want to send. However, for a larger grid, you can have a 255, 246 Hamming grid, I believe it's called. I think 255, 247, sorry. And that will have a far less redundancy, as he talked about. But yeah, this is effectively my implementation of Hamming grids into Minecraft. Anyways, I hope you guys have enjoyed this video, and if you did, then please be sure to check out my other videos, because I actually don't really do similar content to this, but I do other Redstone-y content, and you might enjoy that stuff as well. And if you want to hear about the latest videos, then be sure to subscribe. Anyways, thanks for watching, everyone, and have a nice day.